Everybody, so we will start our second lecture in chapter 24. Okay, so let me remind you of what we have done yesterday, and the way I want to do it, I want to compare gravitational forces and potential energy and electrostatic forces. Okay, so let's okay, you studied in physics 122 or 121 that the gravitational force is equal to mg. Okay, and really it is equal to the gravitational constant, capital G, times the mass of the Earth divided by the radius of the Earth squared times the mass of an object. So the electrostatic force, we said, is equal to Coulomb's constant, K, times Q1, Q2, divided by the distance squared. Okay? Then we did the so here we can write that G, if you want to write the gravitational or G, it's just equal to capital G, mass of the Earth, divided by radius of the Earth squared. And here we also define that electric field is equal K. Let's assume the one is a source, Q1 is a source charge. Q1 is a source charge. So this is K, Q1 divided by R squared. So let me just write it in absolute values. So this is the electric field. In physics 121, you did the work due to a force, and you wrote the work is equal to F dotted with ds. This is for a varying force. In this case, the gravitational force is not varying, so it simplifies to just the gravitational force times the distance traveled. So let's say mg d, or let me put minus mg delta y if we take y to be positive, to be upwards. Okay, we can do the same thing for, so this is the work due to gravitational force, this is the work due to electric force. It's the integral of f of E, the electrostatic force, dotted with ds. Okay, and since F is equal to QE, we know F is Q times E. This simplifies to the integral of QE dotted with ds. Okay, then you defined in physics 121 the change in gravitational potential energy, and you used its minus the work due to gravity. So it's in this case mg delta y. Okay, y is the height, the difference in height. Okay, same thing for the electrostatic force. We can define the potential energy. So this is delta UE is equal also minus the work due to the electrostatic force, and so this is going to be minus QE dotted with ds. Okay, what else? All right, so yes, you did the conservation of energy in physics 121, and you used work due to external forces is equal the change in kinetic energy plus the change in gravitational potential energy plus the change in thermal energy, E thermal, which is due to friction, and so on. Now we can write also the work due to external forces on a system. So if you have a system and you have an external force, obviously in many cases the external force is zero, as we will see today, for example. So now we add another term to this equation, which is the change in electric potential energy. So we can write delta K plus delta U due to gravity plus delta U due to electric field plus all of the other terms. Usually if you're dealing with charges like electrons and protons, the change in gravitational potential energy is negligible. So you can usually ignore this one if it's an individual electron or proton and so on. Okay, So these are the definitions we have done. And now we introduced something else. We said we defined the change in potential, not potential energy, potential is equal the change in electric potential energy divided by the test charge Q. The source charge Q. It's delta U, so we can write that this is equal to minus the integral of E dotted with ds. So we bring this when we divide by Q, which is the source charge, so it simplifies to minus the integral of E dotted with ds. Okay, so this is what we have done last time. Any questions? Okay, clear? Okay, so let me go to presentation mode. Okay, so for a uniform electric field, we can draw the field and we can draw the equipotential surfaces. Remember, we said equipotential surfaces are a surface on which the potential V is constant, or the voltage is constant. So if we draw the electric field lines, we can draw the equipotential lines or surfaces, because you're looking at the side. These are now displayed as lines, but in reality they are surfaces if you go to three-dimensional. Okay, and so let's assume we have an initial position and a final position. Okay, and the distance between them is delta S, capital delta S. Okay, we can display the element vector ds as shown in the figure here. Okay, and now we write delta V, which is V final minus V initial, is equal to minus the integral of E dotted with ds. So this is what we obtained from the previous slide. Okay, now since the electric field is constant and the electric field is parallel to ds, cosine 0 is 1, so this simplifies to just minus E times the total distance delta S. So it becomes simpler, and then we can get the electric field is really minus delta V over delta S. So if I measure the voltage here, V final, and measure the voltage here, V initial, okay, so this is going to be V final minus V initial divided by the distance between these 2 points, delta S. So you can have this in an experimental setup. You can put, for example, I don't know if you're doing this or not, but so if you measure the voltage at 2 points in a field, and you know the distance between these 2 points, you can estimate the electric field, if it's uniform, by doing delta V divided by delta S, and you don't forget the minus sign. Remember, the electric field is pointing always in which direction? Increasing or decreasing potential? Decreasing potential. So we expect that V final, in this case, is going to be V final is going to be less than V initial, because the electric field is always pointing in the direction of decreasing potential. This is the electric field vector. So this is a lower potential. Electric field always points towards lower electric potential values. That's the rule. You can always apply it. All right, let's do this checkpoint, and let me start the Kahoot. By the way, I use the Kahoot, especially the first week. I used the Kahoot for attendance. So if you do not participate in the Kahoot, you are probably marked as absent. But I told you that I will use Kahoot for attendance. Like yesterday, I did not pass attendance sheet. I used Kahoot. So please participate in the Kahoots. So let me go to the Kahoot and let me start it. Save. Okay, play. Start. So everybody please enter the Kahoot. I will use it for okay. The pin is 3414503. Okay, so while you're joining, let me display the question. So let me read it in case you cannot see it well. The labeled points in the figure are on a series of equipotential surfaces associated with an electric field. So we have, this is one surface that has a potential of 9 volts. This surface 8, 7, and 6 volts. A and B are on this surface, C on this surface, E on the middle. I guess it's on the same surface as a 7 volt, and you have D on the 6 volt equipotential surface. The question is, rank from greatest to smallest the work done by the electric field on a positively charged particle that moves from A to B. So from A to B, from B to C, B to C, from C to D, C to D, and from D to E, and from D to E. Okay, so you have choices here. Okay, so let me go ahead and think about it. I'll give you a minute. Okay, so decide between A, B, C, or D. Okay, so I'll start the Kahoot. Okay, we have 10 seconds. Okay, so we have 5 correct answers. We have, and the rest are 21 or 22 incorrect answers. All right, so let's see. This is not an easy one, by the way. I mean, so let's do it together. So, what did we say about the work due to electric field or due to electrostatic force? We said W is equal to minus delta U. We said the change in electric potential energy is equal minus the work, or vice versa. So what is minus delta U? It's minus Q delta U is Q delta V. So minus Q delta V. All right, so let's do all of each one of them. So let's do W A to B. What's delta V for A to B? They are on the same surface, so delta V is 0. So this is 0. Okay, the next one is C to D. C to D, So this is Q, this is a positive charge. Q, what's delta V here? So C to D, so it's 6 minus 7, so that's minus 1, so it's minus Q, and so it's 1 volt, minus Q times 1 volt. Okay, well, C to D minus Q delta V, the positive, we have a positive charge, so it's minus Q times 1 volt. Okay, how about so all right, so we have delta V is 6 minus 7, that's minus 1 times, yes, that's correct, thank you. So that's, yes, thank you, plus QV, I forgot the minus sign. Okay, let's do A to B. B to C. So if we go from B to C, delta V is what? It's 7 minus 9, that's minus 2. Minus 2 times minus Q, that's 2Q. So this is 2Q. Okay, the last one is the work from D to E. D to E. So if we go D to E, so we're going from 6 to 7 volts. Delta V is 7 minus 6, that's 1 volt. So that's it will, so it will be minus Q times 1 volt. So which one is the largest? So 2Q is the largest, that's BC. The next one is what? CD, it's 1Q. Then 0, A to B is 0. Then the last one is D to E, which is minus Q. So the trick is to write the equation and determine what's delta V in all of these situations, multiply by minus Q. Okay, so here we are lucky the charge is positive. If the charge was negative, then the signs will be reversed. Okay, so please be careful about the signs. The charge has a sign and so on. Unlike the mass is always positive. The charge can be positive and negative. Okay, next problem. So here we have a battery, a car battery has a specified potential difference delta V, 12 volts, between its terminal. It establishes a potential difference between the conductors attached to the terminal. So here we have a plate A and plate B. They are connected to the 12 volt battery. Okay, as shown in the figure. The separation between the plates is 0.3 centimeters, and we assume the electric field between the plates to be uniform. Okay, find the magnitude of the electric field between the plates. So if we want to draw the electric field, which way you think the electric field is going? Is it going to go like this or going to go like this? To the left or to the right? The left. To the left, because it goes, remember, electric field always goes from positive to negative, so it is to the left. So this is the correct electric field direction. Okay, and they asked for the magnitude of the electric field. Now we said for a uniform electric field, the electric field is minus delta V divided by the distance D, and since they are interested only in the magnitude, so we can write the magnitude of E is equal to delta V over D. Okay, so delta V is 12 volts and the distance is 0.3 centimeters, so 0.003 meters, and you will be able to find the electric field. So in this case, the electric field is the magnitude of the electric field is 4,000 volts per meter, or newtons, yes, newtons per coulombs, per coulomb. Some simple problem. So you, okay, next problem. Let's assume we have now two plates and an electric field between them. So you can see the electric field is pointing from the positive to the negative plate. A proton is released from rest at point A. in a uniform electric field that has a magnitude of 8 × 10⁴ volts per meter. The proton undergoes a displacement of magnitude d, so it goes from, this is d, 0.5 meters, to point B. So it goes from A to B, thank you. It goes from A to B, okay, in the direction of the electric field. Obviously, because it's a positive charge, we know if there is a positive charge, the force is going to be in the same direction as the electric field, okay. So, and so it will increase the speed. Find the speed of the proton after completing the displacement. Very similar to the quiz problem. I can use the same technique that we use for the quiz. So here, what we can say, we can write the force, the electrostatic force, is equal to the charge of the Q times E. Okay, and since the proton has a mass, we can write this is equal to the mass of the proton times the acceleration A, and we can get the acceleration A is QE divided by M. Since this is a constant force, so we have constant acceleration, and because F is equal to ma, it's constant acceleration, we can use equations of motion at constant acceleration. So we can write V final squared minus V initial squared is equal to times A, the distance d here. So we can solve, since V initial is 0, we can solve for V final. It's equal to 2 times A times d square root. So A is QE divided by M, so that's 2 QE divided by M times d square root of this. Okay, this is one method. I would like to use the conservation of energy method. Okay, so second method, I will use the fact that the work due to external forces is equal delta K plus delta U electric plus delta U gravitation and so on. Here, the change in potential energy due to gravity is very small. You can verify that, obviously, so I will ignore this component. The system of the two plates and the charge, is a system. There are no external forces. So there is zero work due to the external force. So the electrostatic force is internal to the system. It's due to the electric field, so it's an internal force. So that's why the work due to external forces is 0. So that means delta K plus delta U is 0. So let me do delta K. So this is K initial, it's 0 because it starts at 0 in velocity. K final is 1/2 mv final squared. So I can write 1/2 mv final squared minus 0 is equal to minus delta U. Okay, what is delta U? We have an equation for delta U. We said it's delta U, we said it's minus the integral of E ds. So this is minus times minus, so it becomes the plus the integral of E dotted with ds. So we have a minus, delta U is equal minus the integral of E dot ds, but we already have a minus, so minus times minus gives us a plus. And since the electric field is constant, this simplifies to just E times the displacement d. So we can write V final is equal to E d 2 ED 2Q. Yeah, I forgot the Q here. Sorry. It's delta V is equal the integral of minus E dot ds. Delta U is Q times delta V, so I have to put the Q there. So 2Q ED divided by M square root. Same as this one. So if you feel more comfortable using Newton's law and the equations of motion, and if you like, you can use conservation of energy equation. Conservation of energy equation is much more powerful because it applies even if there is no constant force, even if the force is varying and so on. So that is a more powerful method. So when you do that, you find that the final velocity is 2.8 10 to the power 6 meters per second. Obviously, the mass of the proton is 1.67 10 to the minus 27. And this is now 12:24. So even if there is a class later, I don't see, because sometimes I see students just living in the middle of the lecture. You are supposed to attend the full lecture. If you have a class before or a class after, I gave you the permission to come a little bit late or to leave a little bit early, okay? But you are responsible to attend most of the class. So it's not something, it's not a permission to leave and enter at any time. So I leave it up to you. If you leave without an excuse, you are cheating on the attendance. You are marked as present, but you are really not present. So please, I want you to observe this. And I cannot control it because I know some students come late and some students leave early because of other classes. But it is your responsibility. If you have some responsibility, it's your responsibility that you should attend as much as possible of the lecture. You cannot leave and enter at any time, please. Okay, so clear? Is this question clear? So we use two techniques. One is the constant motion, equation of motion at constant acceleration, and the other one is the conservation of energy. Okay, let's make this a little bit more interesting. Now we have an electron in a uniform electric field. The electric field is 1500 newtons per coulomb, or volts per, 150 newtons per coulomb, and the displacement is now 520 meters. So this is the electron, starts here, and then it moves up, because you know the electric field, the force is opposite to the electric field because of a negative charge. So it moves up to this position, and the displacement is 520 meters. What is the change in the electric potential energy of the electron field system? So we want the change in the electric potential energy. Okay, we have an equation for this. We said this is equal QE dotted with ds. Okay, so since the electric field is, let's do step by step. Now notice ds and E are 180 degrees apart. So I can write that this is minus Q E ds cosine of 180 cosine of 180 ds. Cosine of 180 is minus 1. So it will take care of this one. So this is going to be so QE. So since Q and E are constant, I will take them outside of the integral. So that will be QE, the integral of ds. Q is minus E, so it's minus the charge of an electron, times E. The integral of this is equal to D. So this is minus E, which is 1.6 10 to the minus 19, times the electric field, which is 150, times the displacement D, which is 520 meters. So this will be a negative number. Okay, the next question is, through what potential change does the electron move? So we want now delta V. This is V initial, this is V final. So we write delta V, but we know what's the relationship between delta V and the change in potential energy. We said delta V is equal delta U over the charge Q. So this is going to be delta U, which is minus E times E, capital E times D, divided by the charge of the electron, which is minus E. So this will give me ED. Okay, so the change in potential energy in this case is negative, but the change in voltage is positive. And it makes sense because we said the electric field is always pointing in the direction of decreasing potential. So V initial, let's see, did I make a mistake? Delta U, so ED, V initial to V final, potential. Yes, so let me check. Yeah, okay, so here the delta U is minus E, the charge of the electron, times capital E times D. We get minus 1.2 10 to the minus 14 joules, and delta V, which is in this case, when you divide by minus E, you get 45,000 volts. Okay, so 45,000 volts is the change. So be careful about the signs. I know it's a little bit challenging but keep track of the signs. Okay, now we want to determine what is the potential if you have a point charge, a potential at a distance r due to a point charge. Okay, and in order to do that, we want to determine delta V. So let's assume we have a charge Q here, and let's assume you have a test charge that moves from A to B. So we want VB minus VA. Okay, and we're going to use the integral that we defined earlier. We said this is equal to minus the integral of E dotted with ds. Okay, so let's take at a particular point, this is ds, this is the displacement vector. Okay, so let's write this. First of all, we know E for a point charge is given by Coulomb's law. We said it's equal to K Q divided by R squared times the unit vector R. This is unit vector R, so this is not, so this is unit vector. So unit vector has only a magnitude of 1. This is a unit vector R. Okay, so we replaced here in this integral, and we try to determine delta V, which is VB minus VA, is going to be the minus the integral of K Q divided by R squared unit vector R dotted with the displacement vector ds. When we have a dot product between two vectors, you can take the magnitude of each one times cosine of the angle between them. The magnitude of the unit vector is 1. So this here is equal to 1 times ds times cosine theta. Cosine theta times ds. You see, this is the angle theta, this is the unit vector R here, this is ds here. Okay, so I'm going to replace that. So I'm going to write minus K Q divided by R squared. Okay, and so and R ds we replaced by cosine theta. Okay, and yes, cosine theta ds. What is cosine theta ds? Notice this is ds, this is R. Okay, and you can see that the element dr is actually equal to ds cosine theta. So this here is equal to dr. So this is minus kq divided by r squared dr. So this is, and we're taking this from RA to RB. What's the integral of 1 over r squared? Minus 1 over r. So this is, and we have a minus. So minus and a minus becomes plus kq over r evaluated between RA and RB. So this becomes equal kq divided by RB minus kq divided by RA. This is equal VB minus VA. So what can we do? What can we say about the potential? The potential V is just equal kq divided by R. Kq divided by R. If you have a point charge, and if you are at a distance r from the point charge, you can determine the potential or the voltage is kq over r. Notice, first of all, this is a scalar. It's not a vector. It's not like the electric field. The second remark, we don't have r squared in the denominator. We have over r. It's unlike the electric field. The electric field is kq over r squared, and it's a vector. here this is a scalar, okay, and it's 1 over r, not 1 over r squared. In fact, we usually define v at infinity, which is k q divided by infinity, which is 0. So we usually define 0, v infinity, to be equal to 0, or the potential energy at infinity, electric potential energy at infinity, is 0. Remember, when you studied in 121, we said when you're dealing with potential energy, what is important is the difference. It's delta U is the important. So usually you take a certain level and you say, this is my 0 potential energy. And in that course, you took usually the lowest level, the ground level, to be your potential energy equal to 0. For electric potential energy, we take 0 at infinity. So we define the potential energy to be 0, electric potential energy to be 0 when the object is at infinity. And it agrees with the equation. When you set r equal to infinity, the potential becomes kq over infinity, which is 0. But notice the following. It depends on the charge. If the charge is positive, the potential V is positive. But if the charge is negative, the potential is negative. So it's not, well, the electric field also changes direction. If it's a positive charge, it's pointing away from the positive charge. And if it is negative charge, the vector is pointing towards the negative charge. Here, it's not direction, but it is the positive or negative, because the potential is a scalar quantity. So this is what we just have done. We have proven that for a point charge, we can just use the equation. If you're asked for the potential at the distance r, it's just equal kq over r. And by definition, we take the potential to be 0 at a distance of infinity. Okay, so let me go to presentation mode. It's lagging in my screen. It's giving me something dark. So it's here. Duplicate slideshow. Okay. So this is the equation we just explained. The electric potential due to a particle of charge q at a distance r from the particle is equal kq over r. Okay. And so if you have a positive charge, this is how the potential looks like. And notice this is a positive charge. The potential is like a mountain that peaks at the location of the positive charge. Because when r approaches 0, this becomes very large. It never reaches infinity because we cannot have r equal to 0. If you have a charge, you cannot be inside the charge. The point is going to be always outside the charge, so the distance between the center of the charge and the point of interest will never be 0. So it will not be infinity, but it will peak like this. But if the charge is negative, it will actually be a well. So it will be a potential well, and it will go down because it's negative. Let me show you this one here. So we're going to see how the equipotential electric field, and so we will see the potential also to a single and to two charges. I don't know why it's taking too long. Yeah, I think I have it already open here, so let me check if it's working. Okay, it's taking too long. Anyway, let me give it time. It will, hopefully it will work, and let me proceed. Okay. All right. So let's assume you have more than one charge, 3 charges. The superposition principle applies. So the potential due to these 3 charges, please pay attention. The mobile, you use it for the Kahoot only, yeah? Not for other things. Okay, so if we have 3 charges, we can determine the potential at a point from all of these 3 charges. We just apply the law KQ over R, and we add them. It's a scalar addition. It's not a vector addition. So it's a, so in this case, so we can determine V1 is KQ1 divided by R1, V2 is KQ2 divided by R2, and V3 is equal KQ3 divided by R3. Notice Q1 and Q2 can be positive or negative. They can take any sign. The total potential is just going to be V1 plus V2 plus V3. Okay, so it's the superposition principle applies also like we did, except the electric field, there is a difference. The electric field is a vector. So this is an algebraic or a scalar sum. Okay, so this is the equation. Okay, so let me, for n charged particle, we use superposition principle. In this case, the addition of potential, which are scalars, these potentials can be positive or negative. Positive if the charge is positive, and negative if the charge is negative. So this is a general equation. If we have n charged particles, you just add all the potentials in a scalar addition. Okay. So for an electric field, the situation, we have to draw the vectors, and we do the summation of the vectors, vector summation. So we have to determine the x component, y component, z component, and add them. Here you don't have to do that. So the potential is just equal to the a scalar algebraic sum of all of these 3 potentials. Okay, let's do this checkpoint. Okay, so let me go back to the Kahoot. Yes, yes, go to back to the Kahoot. Same Kahoot. Here, before I go to the Kahoot, let me show you this. Okay, so here I have, let me first of all start with a simple view, equipotential view. Okay, so let me put this charge 5 nanocoulomb and the other charge minus 5 nanocoulombs. Oops, okay, minus 5 nanocoulombs. So now you can see the equipotential surfaces. The circles are equipotential lines or surfaces. So if I move the voltage here, you can see the voltage is always and in this case 17 point something, and so the voltage is the same on these lines. If I get closer, the electric field is larger and the potential is also larger, the voltage is larger. This is the positive charge. If I go to the negative charge, notice the potential is now negative. So you see minus 4814. If I move on this line, it's negative. Okay, and the electric field is pointing towards the charge. Unlike here, the electric field is away. Here, it's towards the charge. Okay, so let's display this in 3D view. And let me take the distances to be... okay, so these are perfect now. Okay, so 3D view. You can see the positive charge has a mountain. That's the potential there. The negative charge has a well. The potential is negative, and you can see it in rotate the view. So you can see here. So you very nice illustration of the potential due to positive charge and potential due to a negative charge. Okay, so let me go to the Kahoot and start it again. Not start it, we'll continue the Kahoot. Okay, so Next. All right, so answer this question. So we have a point P and at a distance small d from charge Q1 and capital D from charge Q2 in case 1. In case 2, we have point B, P between these two charges, but the distances are also D and capital D. And in the third case, P is at a corner, Q1 is at a distance small d, and Q2 at a distance capital D. Rank the net electric potential, which is a voltage, greatest first. We did this for, remember before we did it for electric field, I think we did it for the magnitude of the electric field. I want you to do it for the electric potential. So here you have choice A, B, and C. I'll give you 20 seconds to think about it. Okay, ready? So choose between A, B, or C. I will start the Kahoot. Okay. 10 seconds. Okay, we have 8 correct answers. We have 2 who chose D. There was no choice D there. Okay, and we have 17, 19 incorrect answers. So let's look at this here. Okay, so what is the potential at point P in this case? V for the first one is equal Q1 KQ1 or KQ1 divided by the distance, which is a small d. This is V1 plus, let's do the summation, plus KQ2 divided by capital D. So this is for the case number 1. Case number 2, same thing, KQ1 divided by D plus KQ2 divided by capital D. Same thing for the third case, KQ1 divided by D plus KQ2 divided by capital D. So the correct answer is C. Notice it's different from the electric field. When we had the question of the electric field, I forgot, but clearly they were not the same. The magnitude of the electric field was not the same in these 3 situations. So, in fact, if these are 2 positive charges, the electric field here they add, okay, here they subtract, so this is, here they subtract, so the magnitude is less than this one, and here you will have an electric field, yes. So here, let me make sure, this is longer, then this is shorter, okay, and here, so this is shorter, if it's positive charge, so the electric field is pointing away, and it's pointing away like this. So these are electric fields. The magnitudes are different in this case, but if you do the potential is the same. Okay, واضح, clear? Let's finish by this example. I have 1 minute. Okay, so here you have a point P at the middle of a square, and you have 4 charges, Q1, Q2, Q3, Q4, and you're asked what is the electric potential at point P. So here I can just write KQ1 divided by R plus KQ2 divided by R plus KQ3 divided by R plus KQ4 divided by R. Except you have to be careful. Q1 is positive, Q2 is negative. Okay, so you have to account for those. So this one, this term is positive, but this term is negative, and Q2 is negative. This term is positive, and this term is positive, and R is just equal D over square root of 2. And when you do that, you evaluate, you find that this is 350 volts. Very simple. It's just scalar addition, but do not forget the signs. Okay, so I will see you tomorrow. So tomorrow at the end of the class, the student who were absent in the quiz and have an excuse, please try to sit in the front. I will give you the quiz at the end of the class. Tomorrow we'll spend more time solving problems from the previous chapter and also this chapter maybe. Okay, so we'll see you tomorrow, inshallah. Yes. Yes.